Hello and welcome to Tea Leaves Programming. Today we are programming like it's 1979, Haskell for Dilettantes. So today we are going to prepare to work on homework number 3. I am using the CIS 194 Fall 2016 class. You can also use Haskell by Sokoban, which you'll find at the URL on your screen. I would actually recommend for most people Haskell via Sokoban. I think it's going to be a little bit simpler because there is some prep work. If you want to do it like I'm doing it and you want to use these starting points, let's show you. Breitner provides some starting code, and that code has been updated in Haskell via Sokoban to use the current API. This code is not, so the first thing we're going to do before we get into the actual topic of today's discussion is update this code. So to do this, you want to open up Code World, and then you want to sign in and then choose Save As to make sure you've saved it under your account so you can get back to it. I've already done that here, and you can see we're already getting a few errors. So we need to fix those errors. So the first error is that the new version of Gray does not take that argument. So I'm just going to replace it like so. That should reveal some more errors about the use of this term path, which you might remember from our first homework, has been replaced by the term polyline. So I'm just going to quickly replace all usages of path with polyline. I think this is all of them. And then there's one more thing, which is we have this interaction of, you might remember interaction of, the type, the name of the signature changed and the arguments changed. So it changed from interaction of to activity of, and this step argument, which had to do with the time quanta of the activity, has now been removed. Is that all of them? Might be one more here. Yes, text is replaced with the term lettering. Great, so now we have a starting point that will work. You are going to take your code from homework 2, the relevant code to display the person, etc., and move it over to homework 3 before you start it. But we're not actually going to jump into homework 3 right now. That's going to be the next video. This is a lecture video, so what are we going to talk about? Well, in a previous lecture, we talked a little bit about recursion, and we've talked about data types. Today, we're going to take both of those to a new level. We're going to define recursive data types, and then we're immediately going to talk about how to hide that recursion. Recursion is important to understand in terms of how things function, but it's actually not a very intuitive way to think about problems. It's actually, ironically, a fairly low-level set of operations to keep in your human meat brain. Breitner calls abstracting away this recursion wholemeal programming as opposed to piecemeal programming, and I kind of like that. So you might be familiar with list types. Up here you can see we have a list of 1, 2, 3 in the playground, and it's simply telling us that it's of type list. We can define a similar type by ourselves, and in fact Breitner does in homework number 3, and we're going to use it. So let's take a look at what that looks like. So what this says is that there's a new type, its name is list, and it takes an argument. The type is not concrete until we give it an argument. So in some sense, list is not a type, but a list of integers is a type, or a list of doubles is a type. And when you have this lowercase letter in a type constructor, that's perfectly polymorphic. There's no constraints on this. So what is a list? Well, if we look at, let me make a little more room here. if we look at our options here, there are two possible options separated by this bar. The first is it could be the constructor empty in the system-defined list type. This would be nil. Or a list can consist of the constructor empty of some type glommed on to a list of some type. I've added the deriving show here because I want to show how that works. So what does that look like in practice? Well, if we type list, that's going to be an error because that's a type name. It's not a concrete value. What if we type empty? Well, empty is one of the possibilities of a list. Exactly the same as if you're using the system list type of just empty brackets, right? So we can also have this entry attached to a list, and we want to be concrete, right? So let's say, let's do that. Is that a list? No, it's only part of a list because we don't have the rest of the list here. So how do we do that? Well, we can do that. Now we have a list that has one item, one entry in it, tea leaves, and then the empty list. And again, this is isomorphic to this list, which is the same thing as this list. These are all essentially, although I'm using different types here, they're essentially equivalent. What if we wanted to have multiple items in the list? And you can see I'm kind of nesting here. I think that's right. Did I get enough? Do I have too many? I did. I have one too many parentheses. So programming like it's 1979, exactly the same. Exactly the same if I could type. Now, one thing about lists is that, and about polymorphic types, is that once you have used a concrete type, you've essentially bound that polymorphic type variable to that concrete type. So what that means is if I take, let's do it with the system list instead of the one we defined. If I take that 1979 in quotes, that string 1979, and replace it with an integer, we're going to get an error. And that's because the moment we used this reference, this became a concrete instance of essentially list string rather than list T or list A. And the error here is a typical Haskell error that is going to be incomprehensible until you get some more experience. But it's basically saying that it can't get a list of characters out of a number. So first let's write some concrete code. Let's do a very simple function that adds 1 to a number. And so that's going to take a number. I'm going to make it even simpler and say it's going to take an int and it's going to return another int. Right? About as simple a function as you could hope for. And we can test it over here. Let me get rid of that bad one. Good. All right, so let's write code that's going to take a list of numbers and apply this add one function to every item in the list. Extremely concrete example, right? We'll call it add one to list. Yeah, I know I'm not really adding to the list, leave me alone. And so that's going to take a list of int and it's going to return a list of int. And once again, I want to give myself a little more space here. Can I not do that? There we go. That's better. Okay, so what do we need? Well, we need cases, right? So what do we do in the case where we have an empty list? We're just going to return the empty list. Add one, pretend I can type to list. And we'll do that. And then we need a recursive call because without that, it's not actually recursive. Add 1 to list, entry 5 empty. We get entry 6 empty. How about entry 10 empty? Entry 5, entry 10 yields entry 6, entry 11. Okay, so what can we say about this? Well, it does function. We had to think a lot about the structure, the specific details of the recursive structure that we were using. But if we have to do this every time we want to use recursive structures, we're going to go find a different programming language because this is intolerable, right? So how can we abstract this? Well, let's take a look. There are multiple layers of abstraction that we can apply to this function to get something more generic. And in fact, I can see at least 3 off the bat. First off, this thing does one thing. It applies one function. So we can abstract that out so it'll apply any function that would apply to a list of int, right? The second level of abstraction is, why are we limiting ourselves to a list of int? Maybe we should be able to apply any function to any list. The third level of abstraction is maybe this idea of applying a function to a list is more generic than lists. Maybe we want to be able to apply a function to any recursive structure. So let's take these in order. First, let's make this generic as to the function that it applies to a list of int. All right, so we could say, I should have really called this add 1 to list of int, but we'll say do to list of int. And it's going to have the same function because I'm not actually abstracting that. Instead, we're going to add a new argument. I don't want to call that fn. No, it's a type, right? So it could be anything. And we'll bind it to the name function. And we'll do it, right? Any function applied to a list of int. Right. And I know that many of you are already jumping ahead and saying, well, why are you doing this so piecewise? Because I think it provides a good framework to understand what's going on at a lower level. So what do we have here? Now, actually, I bound that to a name. We don't actually need a name because we said no, that anything we apply to empty is empty, right? Entry and list. This is going to look very similar. Only now, instead of saying entry n plus 1, we're going to say entry function n, and then due to list of int function list. I believe that's correct. No, I've got a typo here. Oh, this isn't a typo. This is actually 2 separate bugs. So first of all, since I want this a argument to be a function, it probably should have looked more like this, where I say it's some argument, that's why it's in parentheses, that takes an a and returns an a. But then there's another problem here, which is that a is too generic. If we're applying this to list int, this has to be an int to int, right? So it's fairly complicated, like type signature there, but I think you get it. So now let's take this. I'm going to copy that. We're going to say due to list of int, and the first argument is going to be add 1, which is our function from int to int, and then that, and we get the same result, which is, after all, what we wanted. Okay, so that's a little bit more abstract, but not very, right? The fact that we still have to have this function specified as being from int to int. So really what we want is something that will apply a function to any list. And we call that conceptually mapping. So let's make this function maplist. And its type, it's going to take a function that goes from any type to the same type. And it's going to apply to any type of a list. Okay, I seem to be stuck in caps lock. There we go. Okay, so map list. Anything applied to an empty list is empty as before. Need some more lines here. Oh, also, I don't want my big ugly head to be blocking out. So what are we going to do? We're going to define a function. And again, we're going to apply that function. I'm going to call it x. No, I'm going to call it the head and the tail. And yes, I know that head and tail might be reserved words in whatever language you're thinking of. But here I'm just binding names to items. So this is going to look very similar to what we did before. I need another, I think I do, another close parenthesis. Oh, and once again, I've changed conventions in the type variable. I said this function goes from A to A, and then I said the list was of type T. So those all have to be the same type variable. And just to show you, let's change them. Let's get away from using single letters, which I complain. Let's call it type foo. It could be any type. And this is a list of foo. So give it a function that goes from foo to foo. And given a list of foo, we can apply this to the function. We should be able to do everything we did here, map list, and indeed we get the same results. Now, have we made this as generic as it could be? No, because there's no particular rule that says that we can't take one type and return another, right? And in fact, if we define this to take one type and return another, it will still be valid to take one type and return the same type. I don't know if that was confusing. Let's see if writing the code helps explain it. So let's say we make a new function called genMapList. It's really, I should just call it MapList. I'm going to call it MapList2. Somewhere out there, someone is angry that I didn't use the apostrophe. So instead of going from foo to foo, let's go from foo to bar. So we're going to take a list foo and we're going to return a list bar. Now in some cases, bar might be foo, might be the same, but that's how we're going to define this. And then the rest of this, I think, can just be the same as long as we change the name and change the call. Is that correct? And let's make sure that this works with our case. It does. So there is actually a maximally generic apply something to something that is vaguely container-like. People get mad at me for saying it, called fmap. So what happens if we try and use fmap in this case? Okay, we're getting an error, which is what I expected. Now here is where we start talking about type classes. And this is going to be one of those cases where we're just going to skim off the surface to show you how generic Haskell can get. What we're getting told here is no instance for functor list arising from a use of fmap. So what that means is fmap is a function that is defined in this type class functor. Functor has an implementation, a minimal implementation to use it, which means you need to define this fmap function. You need to define it in a special way. And so let's go ahead and define that. I believe it is, I believe it starts with a capital, right? Nope, it's lowercase. Instance functor lift, where fmap equals, we could literally define, just put maplist2 down here, put the code for it, but instead let's just do this. Right. And now you'll note that our fmap is doing the same job that this extremely specific code back here was doing. So in other words, we have structures in the language that will operate on, I don't want to say maximally generic types, but very generic types, as long as those types implement the instances that those functions expect, that those type classes expect. I believe in the very first episode of this series, I mentioned the Data 61 FP course, and a fair bit of time in that course is spent defining instances to accomplish this very task. And that course goes up to extremely generic areas, heights, very quickly. Maybe sometime I'll do a sidebar episode where we work through some of the Data 61 episodes. This concept of polymorphism, and I know I went kind of deeper into it than I expected I needed to. This is going to be used heavily in homework number 3. This map list function that we wrote is going to be used heavily in homework number 3. And that is where I will see you in the next episode. You've been watching Programming Like It's 1979. The channel is Tea Leaves Programming. Please like and subscribe. If you want to become a member, we have perks for members, and we'd love to have you on board. Thank you so much for watching.